You know how scientists usually agree on big ideas in physics? Well, there's this thing called the Penrose Singularity Theorem that many scientists have believed in for a long time. It's like a rule that says black holes have a scary point at their center called a singularity. But now, a scientist named Roy Kerr has written a new paper that might change everything. He's saying that maybe these scary singularities in black holes aren't real after all. It's like he's questioning a big rule that everyone thought was true. So if Kerr is right, it could mean a big shift in how we understand black holes. A long time ago, Isaac Newton cracked the code on how gravity pulls things. It was a huge breakthrough because it explained why apples fall from trees and how planets move in space. But this discovery led to a new puzzling idea. It hinted that if something is super heavy, it could create something called an event horizon. Think of it like a point of no return in space where even light can't escape. This idea introduced the concept of black holes, which are still a big mystery in physics today because they act in strange ways that we're still trying to understand. When Einstein came along, he added more to what Newton had figured out about gravity. His ideas seemed to support the possibility of black holes, which was a big deal. But it also brought up a big problem for physics. You see, according to Einstein's equations, there's this thing called the Schwarzschild solution. It basically suggests that at the center of a black hole, there's a spot called a singularity. This spot is like a super tiny point with infinite density and gravity. It's so extreme that it creates a clash between Einstein's theory of relativity and another big theory called quantum mechanics. These two theories are like the kings of the science world, but when it comes to the singularity in a black hole, they just can't agree. It's like they're speaking different languages and can't find common ground at that tiny but super important spot. A lot of scientists weren't comfortable with the idea of black hole singularities. It's like they found it really hard to believe or understand. Then, in 1965, a British scientist named Sir Roger Penrose came along and kind of confirmed everyone's fears. He showed that, according to his Penrose Singularity Theorem, these singularities are pretty much unavoidable in general relativity. Now, why is this such a big deal? Well, it's because this clash between general relativity and quantum mechanics is a major headache for scientists. They're like two giants fighting, but neither can win because they just don't fit together when it comes to black hole singularities. So, scientists started hoping for a new theory that could combine both general relativity and quantum mechanics. They hoped this new theory would make the singularity problem disappear, like it was just a weird dream from the past. Recently, there's been some exciting news in the world of science, and it's come from a surprising place. Roy Kerr, who is a big deal in studying black holes, published a paper in December that could change how we think about black hole singularities. Basically, he's suggesting that we might not need quantum mechanics to solve the singularity problem in black holes. To understand why this is a big deal, let's go back a bit and talk about black holes and the Penrose Singularity Theorem. Before Penrose, it was thought that the paths things take in space and time, called geodesics, go on forever. Imagine it like lines on a grid, stretching out forever in all directions. But Penrose showed that inside a black hole, these geodesics don't go on forever. They all end up converging at the center. This idea of geodesics ending is called geodesically incomplete. It's like hitting a dead end on a road, but in space and time. Now Kerr's new paper is shaking things up because it challenges the idea that we need quantum mechanics to understand what happens at the center of black holes. If Kerr is right, it could mean a major breakthrough in our understanding of these mysterious cosmic giants. Geodesic incompleteness is like hitting a roadblock in our understanding of space and time. It creates weird spots where things go haywire, and the usual rules of physics don't work anymore. Penrose's argument was that if geodesics hit this roadblock, it means there's a singularity at play, a point where everything breaks down. But Kerr has a different take on this. He's saying, hold on a second, let's look closer. When Penrose talks about geodesics ending at the center of a black hole, he's talking about a mathematical concept called the geodesic parameter. It's like a measurement we use to track the movement of things along these paths in space and time. Imagine it like driving south and reaching the South Pole. You can't go any further. That's what Penrose means when he says geodesics end. For regular stuff like matter, we use something called proper time to measure this movement. If this measurement hits a limit, It suggests a singularity, because we can't make sense of what happens after that point. It's like a dead end in the fabric of space and time. Let's dive deeper into how Penrose made his case. He looked at how light moves instead of regular stuff like matter. This might sound small, but it's a big deal. Here's why. When Penrose talked about geodesic incompleteness leading to a singularity, he was mainly looking at how light travels. And this idea was so convincing that most scientists went along with it for about 60 years. They thought that according to pure general relativity, which is all about how gravity works on a big scale, there had to be these singularities in black holes. So basically, Penrose's argument had a lot of weight because it seemed to make sense based on how light behaves in space. But now, Kerr is challenging this long-held belief, and that's what's causing all the buzz in the scientific community. Let's talk about another big name in science, Stephen Hawking. He took Penrose's ideas and used them to argue that even the Big Bang, the start of our universe, could be a singularity. He said that if you trace back time using Penrose's geodesics idea, everything eventually comes together at one point. But guess what? Roy Kerr, the same guy shaking up the singularity talk in black holes, had some doubts about this. He wasn't fully convinced by the argument. It's like he raised his eyebrows and said, I'm not so sure about that. This shows that even among top scientists, there can be disagreements and questions about big theories. Let me tell you more about Roy Kerr. He's a physicist from New Zealand who made a big breakthrough in 1963. He came up with something called the Kerr metric, which is like a fancy math way of describing how a rotating black hole works. Now, before Kerr's discovery, there was another solution to Einstein's equations called the Schwarzschild solution, but that one only dealt with non-rotating black holes, which are simpler. Kerr's Kerr metric, on the other hand, tackled the more complex case of rotating black holes. It was a major step forward in our understanding of these cosmic monsters. Let's talk about why Roy Kerr's work is so important. You see, most black holes in real life actually spin or rotate. This is a crucial detail that the Kerr solution addresses. So, Kerr's solution is a big deal because it helps us understand how these real spinning black holes work. And guess what? Roy Kerr himself is a big deal too. He strongly disagrees with the idea of singularities in black holes. That means he doesn't think there's a point of infinite density at the center of black holes like many scientists believed before. He also questions whether the Penrose Singularity Theorem really tells us anything about these supposed singularities. It's like he's challenging some long-standing ideas in a big way. Let's dive deeper into why Roy Kerr disagrees with the idea of singularities in black holes. Remember how I mentioned geodesic incompleteness earlier? Well, that's a key point in this argument. You see, Penrose based his argument on a specific type of path called a null geodesic. These are paths that light follows, because light doesn't have mass and travels at the speed of light. Now, here's where it gets interesting. When we say a null geodesic terminates, it means that it doesn't keep going forever. It has a limit or boundary. For regular stuff like us, we measure our paths using something called proper time. But light doesn't experience time the same way we do. Its clocks don't tick like ours. So we use a different measure called an affine parameter to track light's journey. This affine parameter helps us see how light moves along its path in a smooth and clear way. It's like using a special ruler just for light. And this difference in measuring light's path versus regular objects is at the core of Kerr's objection to the idea of singularities in black holes. Let's dig even deeper into why Roy Kerr doesn't buy into the idea of singularities in black holes. Remember how Penrose's theorem talked about affine parameters being limited inside black holes, which led to the idea of dead ends in space-time called singularities? Well, Kerr has a bone to pick with that argument. He says that these affine parameters don't really give us a clear picture of time. It's like using a wonky clock that doesn't tick the way it should. So, just because the affine parameter reaches a limit doesn't mean time itself stops, or that space-time breaks down at that point. Kerr gives an example to explain this. Imagine if we used a funky math trick like an exponential of coordinate time as the affine parameter. This trick would keep the parameter limited, but time could still stretch from minus infinity to plus infinity. In simpler terms, just because our math says stop here doesn't mean time actually stops. So, according to Kerr, this throws a wrench into the idea that singularities are inevitable because of how we measure things in space-time. He's basically saying, hey, let's not jump to conclusions about singularities just because our measurements hit a limit. It's a pretty bold stance in the world of black hole physics. Roy Kerr's paper is actually quite interesting to read. He doesn't hold back his opinions, and is a bit cheeky when he criticizes the physics community. He's basically saying, hey, you guys are following an idea that's not as solid as you think. He even goes as far as to say that this idea is like a building standing on a sandy foundation, not very stable. You can check out his paper in the description if you want to have a chuckle or two. Now here's another important thing Kerr talks about. He compares the black holes studied in Penrose's paper to real-life black holes. And guess what? Real black holes are a bit different. They almost always rotate, unlike the ones in the idealized scenarios. So, when we talk about black holes in the real universe, we need to use Kerr's math, not the older Schwarzschild stuff. This applies not just to rotating black holes, but also to ones with an electric charge. Kerr's ideas are shaking up how we think about black holes, and it's pretty fascinating stuff. Let's talk more about Kerr's black holes because they're pretty unique. Unlike what we used to think about black holes, Kerr's ones don't have a tiny, super dense point at their center called a singularity. Instead, they have what's called a ring singularity. It's like a loop of super intense gravity, but it's not just a tiny dot. Imagine if you took a point and stretched it out into a ring shape. That's kind of what Kerr's ring singularity looks like. It's this looped strand with super strong gravity, kind of like a twisty black hole lasso. But here's the twist. Kerr says even this ring singularity isn't what we usually think of as a real singularity. It's like he's challenging our whole idea of what a singularity should be in a black hole. It's fascinating and a bit mind-bending, right? Let's talk more about what makes Kerr's black holes so interesting. One cool thing is that in a Schwarzschild black hole, everything falling towards the center is like a one-way ticket. Once you cross a certain point called the event horizon, there's no turning back, and you're doomed to collapse into the singularity. But in a Kerr black hole, things get a bit different and more exciting. Right below the event horizon, there's a region where collapse is still inevitable, just like in the Schwarzschild case. However, once you pass this point, things change. Inside a rotating black hole, the spinning motion creates a kind of pushback against gravity, like when you spin a ball on a string. This creates an inner region where things start to feel almost normal, unlike the extreme pull towards the center. In a Kerr black hole, there's something called an inner horizon. Once you cross it, you're not stuck going only towards the center. You can actually move in any direction, including back up. It's like finding a secret door in a maze. Suddenly, you have more freedom of movement than you thought possible inside a black hole. Isn't that mind-blowing? Let's talk about this ring singularity that Kerr brings up. He basically says it's more of a math trick than a real thing. It's like a tool we use to understand how gravity works around a spinning object. Imagine you have a spinning top, and you see that swirl of motion around it. That's kind of like the ring singularity. It helps us picture the strong pull of gravity around a rotating black hole. But here's the twist. Kerr thinks that if a star actually collapsed into a black hole, it wouldn't turn into this ring shape. Instead, he suggests it would form a stretched-out physical structure inside that inner horizon we talked about earlier. It's like saying the reality might be different from what our math tells us. So in a way, Kerr is challenging our imagination and saying, hey, let's think beyond just the math and picture what might really be going on inside these black holes. It's a fascinating idea that keeps scientists wondering and exploring more about the mysteries of the universe. Let's dive deeper into Roy Kerr's argument and what it means for our understanding of black holes. He's basically saying, hold on a minute. Not all paths inside a black hole lead to a dead end like we thought. You see, according to the famous Penrose Singularity Theorem, all paths of light, called null geodesics, were supposed to end up at a singularity inside a black hole. But Kerr's work flips this idea on its head. He shows that in a Kerr black hole, some of these light paths don't actually lead to a singularity at all. They keep going and trace out different paths inside the black hole without hitting that supposed dead end. This challenges the old belief that once light crosses a black hole's event horizon, it's doomed to get sucked into the center. Kerr is basically saying, not so fast. There might be more to the story. He even questions whether that ring-shaped singularity he talked about earlier is a real thing or just a handy trick in our math. Kerr's ideas are like shaking up a snow globe. They're making us rethink what we thought we knew about black holes and their mysterious interiors. It's exciting, and a bit mind-boggling at the same time. Let's break down what all this means for the idea of singularities in black holes. Kerr's argument doesn't flat-out say that singularities don't exist. Instead, he's questioning whether the way we've been thinking about them might be off. You see, the Penrose Singularity Theorem was like a big stamp saying singularities are definitely there in black holes. But Kerr's research is like saying, hold on, maybe we need to take a closer look. He's saying that just because we see certain limits in our measurements inside a black hole, it doesn't automatically mean there's a singularity. It's kind of like questioning whether a roadblock really means the road ends, or if there's another way around. Now, not all scientists were sold on the idea of black hole singularities in the first place, but many thought we'd need some fancy theory like quantum mechanics to explain what's really going on deep inside black holes. But here comes Kerr's paper, throwing a curveball. It suggests that maybe, just maybe, we can understand black holes without diving into the quantum world. It's like finding a shortcut to solve a tough puzzle without needing all the pieces. So Kerr's work is sparking a lot of excitement because it opens up new possibilities. It's like finding a new clue in a mystery novel that might lead us to a solution without needing to wait for the big reveal of quantum gravity. Pretty cool, right? Let's talk more about what might happen next with Kerr's ideas. Right now, scientists are looking closely at his work to see if it stands up to all the questions and doubts. It's like when you build a tower out of blocks. You want to make sure it doesn't fall over. We're expecting to hear lots of debates and discussions from both sides. Some people might be really excited about Kerr's ideas, while others might still have doubts. It's like watching a big sports game where everyone's cheering for their team. But here's the cool part. If Kerr's ideas turn out to be true, it could change how we think about black holes in a big way. Suddenly, the scary unknown inside black holes might not be so scary anymore, at least from a theoretical point of view. Without those pesky singularities, scientists might be able to come up with better theories about what's going on inside black holes. It's like unlocking a new level in a video game. We get to explore and understand more about the universe without being held back by old ideas. So Roy Kerr's new ideas might just help us navigate through the mysteries of space a little safer and with more confidence. It's an exciting time for physics and our quest to understand the cosmos.